Hello and welcome back. On this episode, we're like a politician who's behind in the opinion polls and we're going to go negative. So, if you remember from our discussion of the comparison test and the ratio test and the root test, we emphasized for maybe what didn't seem like a very good reason that we always needed our series to have positive terms. In other words, they only worked, those tests, if we were adding up positive numbers. If some of those numbers in there were negative, then the test just didn't work. They didn't apply at all. We had to have to do something else. So what else can we do? Well, here's one thing, right? We'll see an example of a series in this lesson with signs that alternate. So these are alternating series, and the reason we call that is because the signs, plus and minus, alternate. So how do we recognize one of these things? Well, if it's written out, as something minus something plus something minus something plus something minus something, that's obvious. If it's written in this sort of short, compact form with a big sigma, right, meaning sum in front of the series, then what you should look for is something like a negative 1 to the k or a minus 1 to the k plus 1 power. What that minus 1 to the k or k plus 1 does, of course, is when you take negative 1 to the first power, you get negative 1. Negative 1 squared will be plus 1. Negative 1 cubed, that's 3 minuses, it goes negative again. So that has the effect of just flip-flopping the signs back and forth from positive to negative. That is assuming that the AKs are always positive, which we will throughout the rest of this set of videos. So here's an example with all the terms written out now, so that the negative ones are in red and the positive ones are in black. This is sort of an accounting metaphor. And so we can sort of see the alternating of the signs, but also something really, really cool happens here if we try to write out what we called several videos ago the sequence of partial sums. So if you remember when we first started talking about series, and we haven't talked about it so much since because we've been doing all these tests, a series will converge if and only if that sequence of partial sums converges. It's like going to the Walmart and scanning your item, beep, putting it in the cart, then beep, scanning the next item, and looking at the subtotal at the bottom. And that list of subtotals that go by, right, that's the sequence of partial sums. If that sequence converges, then the whole series converges. And again, we haven't used that all that much because we had these powerful tests to use. Now we want to go back to that original idea. So first term is a 1. Beep! We scan our 1, and I'm going to put a 1 here on this sort of vertical number line. I think vertical helps a little bit. Next item in the cart, well, actually I guess it's kind of a coupon because when I scan that, beep, that's negative a half. So instead of adding, right, that negative a half takes 50 cents off. So our total drops from 1 down to 0.5. Okay? Then we grab the next item in the cart, beep, we scan that one, that's a third, right? So our total jumps up to like 0.833 something. Okay? But now notice something interesting that just happened. Because the third that we added is smaller than the half that we subtracted, when our total jumps up, it doesn't jump all the way up to 1 or past 1, it's actually a little less than 1. So we've jumped down to a half. When we jumped back up, we only went to 0.83 or so. Okay? Next thing in the cart is another coupon for 25 cents off. Right? We take our negative 1/4, beep, scan that one, and the total is going to drop again, right, all the way down to 0.583-ish. Okay? But again, notice what happened. The drop by a quarter is smaller than, right, the third that we went up by, which means that we don't go all the way down to 0.5, right? We don't go quite that far. We're at 0.58 or so. Grab the next item. That's a fifth. Beep! We scan it, and our total jumps up to 0.7833. Okay? But notice again that when the total jumps up, it doesn't go as high as it used to be, only part of the way up the thing. All right, grab the negative 1/6. So another coupon. Scan that one. Beep! It subtracts off 1/6, and the total drops to 0.616-ish. Okay, and again, notice what's happening. It seems to be zooming in on something, right? This sequence is going up and down, up and down, up and down. But because the numbers that I'm adding are decreasing, right? A half, a third, a fourth, a sixth. Each swing, right, doesn't take us past where we were before, but it swings less and less and less. It's sort of like a spring that's bouncing less and less and less as gravity and air resistance and it just being tired wears on it. And so the swing is up and down, up and down, up and down, but less and less every time. So it oscillates a little less, and it seems to be narrowing in on some sort of a sum right there in the middle. In fact, that's exactly what it's doing. This series, this alternating series, is converging. And it's converging to some number in there between 0.61 and 0.78. The actual sum turns out to be, you might guess it's halfway in the middle. It's not. It's actually about 0.70, 0.70 and some change. The actual number is 1 over the square root of 2. Okay? And why that is, we'll see in a much later video. So what we really have discovered here, though, is kind of a general principle. What we needed to make this work was that every other term to be a different sign, right? So a positive, then a negative, then a positive, then a negative, and that the items that we were adding up, either coupons or items we were scanning that we charged money for, that those numbers we're adding up were decreasing, right? So a half, a third, a fourth, a fifth, a sixth. That sequence of numbers was decreasing. So that the swings up and down got less and less over time. So it's going to eventually, right, start to converge to something in the middle. So this leads us to an alternating series test. If you have an alternating series where the AKs, of course, are positive, and the negative 1 to the k means that the series as a whole is switching signs, plus minus, plus minus, plus minus. If you look at those AKs, so in this case that would be, or in the previous example, that would be like the 1, 1 half, 1/3, 1/4, 1/5, 1/6, and so on. If those numbers are decreasing, right, and the limit is 0, right, so the swings are getting less and less and less, and the total amount of swinging is going to 0, then, just like in that last picture we saw where we were writing out the sequence of partial sums, this entire alternating series will converge. This is really cool. This is a really easy test to apply, right? Because we just look at the thing. If it's obviously an alternating series, we just put our thumb over the sum, like we do when we're doing the divergence test. We put our thumb over the alternator, that negative 1 to the k. We just look at what's left. In the example a second ago, that would be 1 over k, right? 1 half, a third, a fourth, a fifth, a sixth. And see if that sequence is decreasing and goes to 0. That's super easy to check, right? If it is, then this entire alternating series converges. This is probably the easiest test in the world to use. Now, one word of caution here, right? I mentioned a second ago that you put your thumb over the sum, and this is sort of like like you would with the divergence test. It's kind of like the divergence test. In fact, it's kind of like what we're testing is the part of the divergence test that I made this huge flashing red letters, never, never, ever do this. Again, when we talked about the divergence test, we always said that if you try to do the divergence test, put your thumb over the sum, look at what's left as a sequence, and see if that sequence goes to 0. If it doesn't go to 0, the divergence test will tell you that you definitely diverge. If it does go to 0, then it says, sorry, can't help you, go do something else. But now all of a sudden in this example, right, I've got here that the limit is 0, right, and it does tell me that it converges. What's going on here? Well, the difference is, of course, this is an alternating series. This only ever works if we have an alternating series. If we have something else, right, it's not an alternating series, then this sort of backwards way of doing the divergence test, will still get you in big trouble if you try that on an exam. In other words, if you have an alternating series, you put your thumb over the sum and the alternator and look at just the sequence. If that goes to 0, we converge, we're good. If we were to try that with something that wasn't alternating, put our thumb over the sum, and it's not an alternating series, then just knowing that the limit goes of the sequence goes to 0 doesn't tell us that the whole series converges. Remember? Okay, let's look at an example. This guy, well, it's the one we were doing before, negative 1 to the k and 1 over k. So as we saw the sequence of partial sums, as we scanned the coupons, beep, there were negative numbers, and the items in the cart that were charging us, beep, that sequence of partial sums will go up and down, up and down, up and down. And because the amount that they swing by is decreasing, 1 over k is a decreasing sequence, and that sequence is definitely going to 0, 1 over k goes to 0, this entire alternating series converges by the alternating series test. Okay? All right, let's try another one. So if we put our thumb over the sum and our thumb over the alternator, right? In other words, we ignore the sum and the negative 1 to the k, and we just look at the rest of this, 3k over 4k minus 1, and look at that sequence. Is that sequence decreasing, and does that sequence go to 0? Well, no, that sequence does not go to 0. It's 3k over the 4k minus 1. We can ignore the minus 1, right? The limit will just be 3/4. So because this sequence doesn't go to 0, it's actually the divergence test that'll tell us this guy diverges, right? Because we always know from the divergence test, if my sequence I'm adding up doesn't go to 0, there's no way that the series can converge. Here's one more. This is a little more complicated looking one with a k squared over k cubed plus 3. But again, it's obviously alternating because of the minus 1 to the k. So all we have to do is look at the rest of the sequence. The k squared over k cubed plus 4. Is that decreasing? Well, yeah, and it's going to 0. By the way, the decreasing part I'm pretty flexible on. If you look in the textbook, they'll say, well, to be sure, maybe we should, replace the k's with x's and take its derivative and see if the derivative is always negative. I mean, this is pretty obvious, right? The k cubed is higher on the tower of power than the k squared. It's dropping like a rock. Right? This is definitely going to converge to 0, and it's decreasing as it does it. No big deal. So that part, at least, you can usually just look at and tell. So converges by the alternating series test. Now, there is something that's going on in the first and the last example, if we think about that for a second. Because obviously, this first example, well, it really even has a name because it's sort of obvious what this is. If the negative 1 to the k weren't there, I just have the series 1 over k. That's our friend, right? We've known that for a long time. It's a p series with p equal to 1, better known as the harmonic series. So this whole thing with the negative 1 to the k in front of it is often called an alternating harmonic series. Boy, that's clever, isn't it? So it converges, right, with the alternator there. But here's a really interesting thing to think about. If I put my thumb over just the alternator, right, and got rid of that, so I look at the sum of 1 over k without the negative terms, right? So if I didn't have the negative terms in there, in other words, if as I scanned, I just scanned items, not coupons. So I scan a 1, beep, then I scan a half, beep, then I scan a third, beep, and the price is all going up. I've just got the harmonic series. That guy diverges. Right? So this series as an alternating series, the one there on the screen, will converge, but it only converges because half the terms are negative. In other words, what's making this guy work is that I'm subtracting half the time, right? So I'm adding up these terms, but half of them are negative, or another way to say that is I'm adding up and then subtracting and adding and then subtracting, adding and then subtracting. Okay, well, that makes it really easy in some sense for these things to converge. But if all the terms were positive, well then, that wouldn't converge at all. Same thing's true for that last example. If you look at the k squared over k cubed plus 4, that guy, well, if I just had that without the alternator, that looks like a limit comparison test problem with a 1 over k is what you compare it to. That guy's going to diverge too. So something is definitely happening with these sort of alternating series, because it's much easier it's much easier to converge if you're an alternating series, because you're subtracting half the time instead of adding. So what we need is some way of separating out the real deal from the fakers. In other words, what we need is some way of saying, you know what, you are really awesome. You would converge even if all of your terms were positive. Even if you went through and you made all the terms positive, you'd still converge. That would happen if you had like negative 1 to the k times 1 over k squared, let's say, right? That guy's converging even if all the terms were positive. But the alternating harmonic series only converges with help, because half the terms are negative, right? Because it's adding and then subtracting and adding and then subtracting. So we really need a way of saying, what's converging because the numbers are getting really, really small, and what's converging because we're subtracting. Right? And that will lead us to our next video and a new definition.